This video gives a step-by-step commentary for one of the processes created after running one of the wizard templates, in this particular case the churn example. Now, the new wizard feature provided with Rapidminer 6 allows processes to be created quickly for a number of typical uses encountered in various industries. These processes give easy to understand results, and the process is actually pretty good practice and shows some interesting techniques, and so this video gives a step-by-step commentary through one example, the churn example, to explain how it works. So what we'll do is we'll run the wizard first to create the process, then we'll step through it. So you run the wizard by doing this. You click this button here and you choose the one you're interested in, churn in this example. I'm going to use demo data. And you're presented with the following decision really. Which column in your data, which is shown here, represents the churn label? Churn being something in telecoms where subscribers defect to another company or competitor. So what you're doing here is indicating whether which of these columns, which of these attributes rather, is the label, and you're saying which is the positive class, i.e. which of them is churn yes. It's sort of obvious, but it's worth stating it because it does affect how the process runs. Having then chosen those, you run this and it will create a process and show some results. And it does this, it's quite cool, and it shows, obviously this is the input data, and you can click on these various little got it buttons to progress through. I'll just click them all actually so we can do it at our own pace. So basically you're seeing here, this is the input data. This is an estimate of how accurate the model that will be created should predict when it sees unseen data. And this is the model in fact here. This lift chart is again, it's similar to the estimate here. It's basically saying if the model sees unseen data, how well will it do? And by virtue of this lift chart saying essentially that it's seeing 90% of the churn examples when the confidence that its prediction is high, you can see that it's distinguishing between churn and non-churn examples quite well. Not perfect, it never is. If we scroll down, also the process is showing the most important attributes that predict the churn label. So basically there are, if we scroll up here, there are 5 regular attributes, and if I scroll down, they are represented here, and the most important two are transaction count and region code. And basically the process has concluded that these two here are the most important. These two predict best whether a customer will churn or not, and the others are less important than they're shown here. And then this then shows, this graph here shows a plot, and it's showing transaction count as one axis, which is this attribute here, and region code as another axis, and it's colouring the points in based on whether they churn or not. And this is basically based on an analysis of training data, because obviously it knows the answer whether a churn happened or not. You can sort of see the colour of the points is coloured red if the model is relatively more confident. So you can see here there's a sort of area where transaction count and region code seem to come together in a sort of contiguous area where the model is relatively more confident that churning will happen. Now all of this view here is done by some method that I can't get hold of, but what I'm going to do is go through the process, which we can see by clicking this button here, that generates the raw data, or in some cases these pictures, that will then ultimately be displayed in this view here. You can export this using the export result dashboard here. That just makes an HTML page containing the data that you're seeing here. But anyway, without further ado, let's try and show the process. So this is the raw process I've just created. For the sake of this video, I'm going to go to one I prepared earlier, which moves it all into a smaller space to make it a bit easier to see. Okay, so first thing, the process is here and it takes an input, and we have to look at the context to see what that means. So I shall make the context happen here. So the context contains an example set contained in the repository. Now this has been done for me in the demo data, and you can see its input, date, time, etc. and it happens to be this one here. So this data will be connected to the input port of the first operator inside the process. In addition, you'll see there were some other macros have been set in the context. Label churn, positive and negative class. If you remember, we chose churn as the attribute, and we said the positive class is yes. So in other words, if the attribute churn is set to yes, then that means obviously the customer will churn. Okay, so let's go back to the overall process. So what's going to happen first is that this operator will filter the input data, and this top output will contain essentially all of the examples which have no missing labels. The bottom row will contain the original data. So let's just look at that data, set a breakpoint on it and have a look. So this is the original unfiltered data. It's got 200 examples and it's got data. So some of the labels are missing. The top row, the top output rather, that has 180 examples, and now none of the churn attributes are missing. You can see that here. So this is what's happened. The process has divided the data into a training set, and the original here is the full data. There's going to be another filtering here. If I set a breakpoint here, this filtering will actually only let through missing labels. In other words, any example with a missing label will make it through here. This was going to become the test data. If I set a breakpoint here, you'll see that there should be about 20. There are 20 examples where churn is missing and all the rest are just normal regular attributes. Okay, so the next thing that's going to happen, this subprocess does a cleaning operation. If I click onto the subprocess, you can see it removes useless attributes. Basically, it's going to remove any attributes which are identical for all examples. It's also going to look at nominals, and if it sees a nominal that is not present in, that is present in less than 10% in this case of the examples, then that nominal is useless. So I suspect that's a rather defensive measure if it ever gets presented with new data. And then replace missing values will essentially replace all numeric values with an average for the entire example set. That processing is also applied here. Remove useless, replace missing with averages. So essentially what's happening, the same processing, or pre-processing to be precise, is being applied to both the training and test sets. I think if I'm honest, I might move this clean input data to before the split operation that's happening here. So this split operation is basically going to partition the training data into a 60%, 40% partition. 60% is being clean. I think I would also, like I say, clean the 40% as well, but I won't do it for now. But if I had to, I would move this to here. Anyway, the 60% of the training data is being passed to a decision tree where a model will get built. The remaining 40% gets passed to the create lift chart. Now, create lift chart requires a model, in this case a decision tree, and data. And it needs to see data with a known label so that it can draw its lift chart. And it's doing this the right way because 60% of the training data has been partitioned up this, and that's what's being used to build the model. The remaining 40% is being passed as unseen. This means the create lift chart is going to do a reasonably good job about estimating the performance on unseen data. But let's look at the create lift chart. So I'm going to set a breakpoint after it. And what we'll actually get output from this, the example set, which is the 40% of the training data, the model, which is the decision tree built on 60% of the data, the training data, and a lift chart. I'll run that. We should see three things. So here's the lift chart. Before we look at that in detail, here's the decision tree, here's the example set, and this is the 40% of the training sample. The lift chart is basically saying that when the confidence that the decision tree model has is between 0.8 and 1, then 18 out of the 20 churns were predicted correctly, and between 0.6, 0.8, 0.2, 0.4 and 0 and 0.2, you can see there are reasonable degrees of success, but basically when it's confident it gets it quite right, when it's not so confident it gets it wrong to a greater or lesser extent. But this gives you a sense, really, this lift chart, as to how well the model is performing. So if we go back to the design view, now what happens next is, right, let's pick this top path. This compute attribute importance subprocess is basically going to do a weight by operation, weight by information gain in this case. And this is basically saying, working out the weight of each attribute with respect to the label. In other words, how good or bad is the attribute in predicting the label. So that's what this operator does, and it's basically going to create some weights, which is this output here, and then I'm going to see that turned into an example set by the weights to data operator. Here's a cunning bit. Next, what happens is that two macros are extracted from these weights. So what essentially will happen is that a macro called scatter x will be set to the value of the attribute which is most predictive of the churn label. The second extract macro does essentially the same thing, but for the second most important. If I set a breakpoint here and look at the macros, we'll see scatter x and scatter y. So before we do that, here this is the weightings that each attribute has in predicting the label, and you can see transaction counter, region code are the most important. If I look at the macros, if I bring that up here so it's a bit easier to see, and you can see scatter x and scatter y are set correctly. So that's quite a neat way of doing that, actually. So let's go back to the process, clear that breakpoint, go up. So this subprocess has worked out the two attributes that are most predictive of the label. It's important to say that it's done that based on the examination of actually only the training data, in fact only 60% of the training data, which may or may not be correct. I might perhaps done it on 100%, but anyway, it doesn't really matter too much. But so this prediction really about the attributes is available here in macros, and I think what happens at the end of the process, those macros get used to plot graphs and so on. This operator here is going to repeat what the create lift chart does. It's going to apply the model to the 40% of the training data that comes out of this split here. So just to recap, the 60% of the training data has been used to make a decision tree. We've got a lift chart from that. We've got some we've got some attributes which are most predictive. Now we're going to actually apply the 60% training model onto the 40% training data, which is what this process, this is what this operator does here. And this is going to actually allow us to extract some data from that operation. If I click into here, this is doing a performance, to be specific, the performance by nominal classification, and certain of the metrics have been ticked, like area under curve, precision recall, and so on. What happens is this performance operator creates a performance vector that gets passed to the performance to data operator. Then an extract macro is done to extract specific rows, specific examples from the example set. It turns out the first one is the accuracy of the performance operator. The second one, this is the area under curve. The third is recall. Fourth is a tidying up, really, of a couple of the other attributes. Sorry, a couple of the other macros, to be precise. But if we set a breakpoint there and run it, you'll see a performance vector, and we'll look at some macros. So here's the performance vector that's output from the performance binomial classification operator, basically saying, for example, that the accuracy is 76%, the precision is 87.5%, and so on. If I now look at the macros, again, we should see. There we go. That's a better view. You should see now the accuracy, area under curve, recall, and so on. These have all been produced as values that can be used later. Let's go back to the design view. So the final operator here is a subprocess, and it does a branch. The branch basically is based on a condition, which is the minimum number of examples in the applied example set. So in other words, if the number of examples is 0, the else part of this branch will execute, otherwise the then will go off. And the branch basically has this part does some tidying up of the example set that's returned. This just outputs an error essentially in the attribute name. It says notice, and the value is something helpful. But anyway, the then part of this, what it does, if we just refresh our memory, let's go back to here. So the apply model has applied the 60% training data model to the unseen test data, and it's filled in a label, and it's also filled in a confidence, and that's what gets passed to this part here. If we go down here, now what that will do is it's going to first of all sort the confidence yes in decreasing order, so the most confidence will be at the top. It's going to do a custom filter and will eliminate everything where the confidence is less than 70%. The rename just changes names to make it more readable. Select attributes. This is slightly more complicated. The label macro is churn. Here it is. So this is basically going to select everything called churn, including something called a special attribute. And it's going to invert it. So in other words, delete. What this will do is delete everything. It'll delete churn and select everything else. And then the final one. This is a similar thing. Except in this case, the label. In this case, the attribute is called confidence bracket no, which is what this will expand to. So the result of this is that certain of the attributes will be deleted from the final example set. So if I just run this, we'll see that happening. Yeah, here is the result of all of that. So the confidence is greater than 0.7. Prediction is yes. We were sort of looking at the lift chart, I guess, and these we can be reasonably confident that these are good examples where the prediction that churn's happening is reasonably good. Not only is the confidence high here, but if we look at the performance on training data partitions, so that the training and test data in that context were never applied to one another, you can see it's basically saying 87.5%, 80%. It's about 80 to 90% confident that these numbers here are that these predictions here are good, and especially if you look at the lift chart. Basically, if you're in the 0.8 to 1 confidence range, you can be pretty sure you're 90% there. So by making the confidence threshold quite high, you can take advantage of the performance of the model as it's more and more confident. So, okay, let's go back to the process. So with this happy note, let's just go back for one last look at the process. There it is. And going into the data, we can have a quick look at some of the different examples here, different tabs rather. Okay.